This lesson is titled Identifying Linear Functions. Our objectives are to provide a definition of linear functions and to identify linear functions from graphs, tables, and equations. A linear function is a function whose graph is a straight path. Mathematically, we say a graph whose points represent a constant rate of change. The phrase constant rate of change is synonymous with slope, and it means that the rate of change will be the same between any 2 points of the graph. The slope formula can be expressed in a variety of ways. Let the variable m represent the slope of a line, and let there be 2 points whose coordinates are, for point 1, x1, y1, and for point 2, x2, y2. Then we can define the slope formula in the following ways. We can say that m, which is the slope, is y2 minus y1 in the numerator over x2 minus x1 in the denominator. This can be expressed in another way, where we say m, which is the slope, is the change in y values over the change in x values. And the third common way is to say m, which is slope, is rise over run. Each of these formulas are the same, they're just expressed differently. It is important to be familiar with all the ways that slope is expressed so that we can better solve real-world problems that use phrases like constant rate of change or rise over run. Here are some examples of graphs. On the left side, we have 2 graphs that represent linear functions. Notice that the points in the first graph are all laid out in a straight path. And the second graph is a line that is going across in a straight path. The next 2 graphs are nonlinear functions. Notice if you follow the points, they do not follow a consistent path. There is some change in direction. And the fourth one is a continuous path, but that curves. In summary, we can identify linear functions by their graphs. There is either a straight line or a straight path of points. If there is any change in direction or curving of the path, then the graph is nonlinear. Now that we know how to identify linear functions by graphs, we can now turn our attention towards identifying linear functions by their data sets and by their equations. Linear data sets can be represented as lists of points or as a table of values. Either way, we can identify whether a data set is linear or not by evaluating the slope between every pair of points. If the slope is always the same, then it is a linear data set. If the slope is different in just one instance, then the set is nonlinear. So example 1 gives us this table to consider. And we can analyze this data by calculating the slope between each pair of points. So remember, slope is equal to the change in y values over the change in x values. So we can look at this first instance, and we see that the first change in y would be 3 minus 5, and the first change in x would be negative 1 minus 0. So this will give us our first slope. 3 minus 5 is negative 2. Negative 1 minus 0 is negative 1. A negative divided by a negative is positive. So our first slope calculation is 2. If we look at the next pair of points, our delta y is 5 minus 7. And our delta x is 0 minus 1. 5 minus 7 is negative 2. 0 minus 1 is negative 1. Negative divided by negative is positive. We see that the slope value is still the same. And we can do this throughout for every pair of points. And I will leave that for you to verify that each and every time we will get a slope that simplifies to 2. Since the slope is always 2, this means that this data set is linear because it has a constant rate of change. Remember, constant rate of change means slope. And since the slopes are the same, they are constant, and there is no change in direction. Here in this second example, we have another set of points that we can look at, and each of these pairs that are being calculated as delta y over delta x will give us 21 over 3, 7 over 1, 14 over 2, and 28 over 4. When you simplify each of them, all of them simplify to 7 over 1. And since they all simplify to 7 over 1, we have a constant rate of change. And since we have a constant rate of change, we can say, therefore, this data represents a linear function. So here's our third example, and you can see that we're going to get that the slopes are not equal. So let's work through this and see the result. 7 minus 4 over negative 2 minus negative 1. Notice the double negative. 7 minus 4 is 3. The double negative becomes a plus, so negative 2 plus 1 is negative 1. We get a slope of negative 3 for the first slope that we calculated. Slope number 2, we have 4 minus 3 in the numerator, and we have negative 1 minus 0. 4 minus 3 is 1. Negative 1 minus 0 is negative 1. And as soon as you get a mismatch, you can stop. You don't have to do the rest of the calculations. At first mismatch in slope values, we can say that the data is nonlinear. Because we do not have a constant rate of change, we have a varying rate of change, meaning we're getting different slope values. And varying rates of change are nonlinear. Constant rates of change are linear. Another way to identify linear functions are by their equations. Linear equations can be expressed in a variety of formats. However, the simplest way to contextualize linear equations is as a first-degree equation. A first-degree equation is one where the variables in the equation have an exponent of positive 1, and none of the variables are multiplied together with one another. So examples here are x equals 3. The variable, even though no exponent is shown, when the exponent is not shown, it is assumed to be a positive 1 in the exponent. Y equals negative 1, again, assumed a positive 1 exponent. Here we have y equals 3x minus 7. We have two variables, both with positive 1 exponents, and none of the variables multiply one another. So that's good. 2y plus 4y equals 8. This could be simplified to 6y equals 8. Again, the variable has an exponent of 1. Or we can have x plus y plus z equals 1. Again, the variables are not multiplying each other. They're just adding. They all have exponents of positive 1. So they are all linear equations. Nonlinear equations have exponents not equal to positive 1, or can be equations that contain products of different variables. So y equals negative 1, we see the exponent is not equal to positive 1. You will learn in other courses that when there's a negative exponent, it is actually a fraction. And we cannot have variables in the denominator of a fraction that is non-linear. Here in the second example, we have x times y. We can't have that because they boost their power. X to the first and y to the first. This means it's not linear because you have two first-degree variables multiplying each other. The third example is nonlinear because of this first term, the x squared. If this term did not exist, it would be linear, but since we have an exponent of 2, this is nonlinear as well. When you have a radical, the square root is the same as putting a fraction exponent. Again, that's something you will learn in later courses. So when we have a radical, we say that is nonlinear. And when we have a fraction, we say that is nonlinear because the exponent is not a positive 1. So that fraction in the exponent is no good. So in summary, we can identify linear functions by their equations. If the variables have exponents of positive 1, the variables cannot be multiplied together. The variables cannot appear in denominators. Variables cannot appear in exponents, and there can be no radical signs around the variable. So this is the end of this lesson. You can go back, replay it, watch it again, take your notes, and then continue by doing the practice and submitting that.